In this class, we will discuss about inductance of a coil or for a pair of coils. We learned earlier that when a coil is kept in a changing magnetic field, an EMF is induced, due to which a current will be induced. Inductance of a coil or for a pair of coil depends upon the current changing in the coil or in the nearby coil. So there are two types of inductance which we are going to discuss. One is mutual inductance and another is self-inductance. The magnetic flux of a coil depends upon the current that is passing through the coil, or the magnetic flux linked with a coil depends upon the current that is passing through the nearby coil. Now, if the coil has n number of turns, the total flux linkage is called n times phi. This is called as flux linkage. Flux linkage. And this is proportional to the current that is changing in the coil itself or the current that is changing in the nearby coil. So this proportionality constant, we may write something like some m times I. This m, that is the proportionality constant, is called as inductance. Inductance. So the units, SI units, are from this. This is flux is expressed in Webers, and hence you bring that current here. Therefore, Weber per ampere is the unit. Weber per ampere is the unit, and 1 Weber per ampere is called as Henry. So the name of the unit Henry is given in memory of the scientist Henry. Okay, so that is about the unit. Now let us discuss about the mutual inductance. Of two coils. So this proportionality constant when defined for two nearby coils, then we call that proportionality constant as mutual inductance. And if it is defined for the same coil, then it is called self-inductance. Consider two coils like this, very long solenoids wound one over the other. Let us suppose this is a coil, say S1, and the radius of this coil, let us take this radius as R1. Now, over this, suppose another coil is wound. So, this is another coil. So, call this as say S2, solenoid S2. And the radius of this be R2. Let L be the length of the coils. Now, if a current I2 passes in the coil S2, then it will create a magnetic field. The first coil S1 is immersed in the magnetic field produced by the coil S2. Similarly, if a current I1 passes through the coil S1, it will produce a magnetic field, and this magnetic field will be inside the first coil, and that will be near the axis of the second coil. So we can calculate we can find out the formula for mutual inductance with respect to the first coil or with respect to the second coil. So let us suppose the magnetic flux linked with the first coil when a current of I2 passes through the second coil. So what is I2? I2 is the current that is passing through second coil, which will produce a magnetic field in which the first coil is immersed. So the magnetic flux linkage with the first coil is given by the magnetic field produced by the second coil and the area of the first coil, because the first coil is immersed in the magnetic field. So this gives the total flux linked with the first coil. But we know that B2 is given by, we use this formula mu naught Ni. So for a magnetic field inside a solenoid, this is the formula we derive. Since we are talking about the magnetic field produced by the second coil, so we have to take the number of turns in the second coil, current passing through the second coil. And since there are the number of turns, so here you have to, the total flux means this is the flux, and multiplying with the number of turns, you have to multiply with the number of turns also. Suppose if there are N1 turns per unit length of solenoid S1, then your N1 will be is equal to capital N1 will be small n1 into L. Therefore, so this N1, this is the magnetic flux. Since there are total number of N1 turns in the primary coil, or that is the first coil, so the flux multiplied with the number of turns. So hence N1 phi1 is given by small n1L, that is the number of turns, and the magnetic field produced by the current in the second coil mu naught N2 I2, and the area of the coil, that is here we have to take the area of the first coil, that is pi R1 square. So therefore we can write like this: mu naught N1 N2 L R1 square I2. So like this you can write. But we have seen that the flux linkage is given by a constant times the current. Therefore, this N1 phi 1 can be written as, here the magnetic flux linked with the first coil with respect to the second coil. So the magnetic flux linkage with the first coil due to the current in the second coil, and here the current in the second coil. So therefore we can say that M12, that is mutual inductance of first coil with respect to second coil. So that is mu naught N1 N2 L R1 square. Okay. And similarly, from the first coil point of view, with respect to the first coil, what is the mutual inductance of the second coil can be calculated. So like this we can do. That is, suppose the magnetic flux linked with the second coil. So that is the total magnetic flux linked with the second coil due to the current passing through the first coil. Let us suppose I1 is the current through the first coil, due to which a flux is linked with the second coil. But here the magnetic field will be inside the first coil, which is immersed in the second coil. So here N2 means that you have to take N2 into L, where N2 is the number of turns per unit length of S2. And the magnetic field here, the magnetic field is produced by the current in the first coil, and hence the current passing through that first coil you have to take. So that is the area of the first coil you have to take. So here B1 is nothing but mu naught N1 I1, and what is A1? That is the area of the first coil you have to take, because magnetic flux will be in the first coil itself. So that is pi R1 square. So N2 phi 2 is equal to, this is N2L, the magnetic field produced by the current in the first coil into area of the first coil. You should not take the area of the second coil, you have to take the area of the first coil itself, because it is inside the second coil. So again, when you write like this, mu naught N1 N2 L R1 square into I1. So this can be written as the mutual inductance of the second coil with respect to the first coil. So into I1. So therefore this is mu21. So that is M21 is nothing but mu naught N1 N2L R1 square. So you will see this M21 and M12 are same. Therefore M12 must be equal to M21. That means mutual inductance of first coil with respect to second one, or mutual inductance of the second coil with respect to the first one are same. So that is equal to, say, M. So M is equal to mu naught N1 N2 L R1 square. So from this you can understand that it depends upon the geometry of the coils and the intrinsic property. Here, how do you say intrinsic property? Means suppose if the coils are wound on a magnetic material like iron, which has high permeability, the magnetic field will be very strong. Suppose if mu r is the relative permeability of the medium that is present between the coils, then M can be written as relative permeability of the free space, number of turns of first, second, length of the coils into this square of the radius of the first coil immersed in the second coil. So that gives the mutual inductance of the coils wound one over the other. Here we neglected the edge effects, considering that the radius of the coils is far less than the length of the coils. So that's why we took coils which are very long and whose radius are very small compared to their lengths. So in that way we can find out mutual inductance of two coils wound one over the other. Suppose if you have one coil kept nearby another coil in which the magnetic field is changing. So you have seen in the previous example, that is, so C1 is a coil which is connected to a galvanometer, C2 is connected to a battery. So if you press the key or if you remove the key, current is induced in C1. That's what you have seen. So in such cases, we can say that the mutual inductance, that is, let us suppose N phi. So that is equal to the mutual inductance multiplied with the current that is changing in the second coil. Therefore, we know induced EMF is given by minus d by dt of N times phi. So that is equal to minus d by dt of N times I. So that is equal to M into di by dt. So the flux link, that is the induced EMF in the first coil, depends upon the rate at which the current changes in the second coil. Okay, so this is the proportionality constant, which we call it as mutual inductance. So it depends on the geometry of the coils and the orientation of the coils, distance between the coils, and the intrinsic properties of the medium present between the coils. So that is about mutual inductance. Then we will talk about the self-inductance. Self-inductance is due to the magnetic flux changing because of the current changing in the coil itself. So self-inductance. So we know that the magnetic flux, suppose if there are total Catalan number of turns and flux through each turn is phi, say phi b. So this is proportional to the current. So N times phi b can be written as some constant times Fi. Here L is the symbol used for self-inductance. So this is self-inductance. It has the same units and dimensions of mutual inductance. So when the current in the coil is gradually increasing, the magnetic field associated with the coil also will be increasing. So the coil itself in a changing magnetic flux. So that magnetic flux will induce a current in opposite direction, so as to decrease the current that is flowing in the coil. Suppose if the current is decreasing, the magnetic field associated with the coil also decreases, producing an induced EMF or induced current that will try to increase the current. So that is in the reverse direction. So therefore, a self-inductance of a coil is something similar to the inertia in mechanics. So which opposes change in the motion of a body. Either the body may be at rest or in uniform motion. We learned that mass is responsible for inertia in mechanics. Similarly, self-inductance is analogous to that, and we can call it as electrical inertia. So that is, if there is a current increasing in the coil or in the circuit, due to induced EMF, a current in opposite direction will produce, trying to decrease the increasing current. And if the current is decreasing, an induced EMF will be producing a current that will try to increase the current. So that's why we call this self-inductance as electrical inertia. Now let us find out a similar formula as we did in the case of two coils, one bound over the other. So that is given by the magnetic field, that is flux is VA. Of course, cos theta is 1. So this is magnetic field produced by the current in the coil. A is the area of the coil, and the number of turns in that coil. So we can say that is say some N. So B is given by mu naught Ni. So that is a formula. So let us take that area as A, or otherwise you can take it as pi r square, where r is the radius of the coil. And number of turns is N into L. Here small n is the number of turns per unit length, and suppose there are small number of turns per unit length, and L is the number of length of that coil, then NL will give you this capital total number of turns in the coil. Now, so that is equal to mu naught N into N square AL into I. So let us compare this equation with this equation. So comparing 1 and 2, because this is the total flux linked with the coil, and this is also total flux linked with the coil. Both are same. Hence 1 and 2 are same. Therefore, we can say that L is equal to mu naught N square area of the coil into L. So that is the formula for self-inductance, and you know self-inductance is also known as back EMF. Back EMF. So as I told you earlier, because it is similar to the mass causing inertia to the increase or decrease of the current in the coil, hence the self-inductance can also be called as back EMF, because it is trying to reduce the growing current or trying to increase the decreasing current. So that's why it is called as back EMF. Now, because of this back EMF, to increase the current in a coil, some work is to be done. So that work done is stored as magnetic energy in the coil. So something like potential energy. So magnetic potential energy or magnetic energy. So the work done against the back EMF to increase the current in a coil is stored as magnetic energy. So let us derive the formulas for this magnetic energy. So energy stored in coil, in which a current is passing through it, and due to back EMF or due to that self-inductance, some work is to be done. Let us suppose at any instant, let I be the current, is the current in the coil. At an instant, suppose this is the current at an instant, therefore we can write like this. So d n times phi by dt is equal to, so this is di by dt. Of course, you know that L is the constant of proportionality. So I can write this with a negative sign, minus L into di by dt. And we know this the changing magnetic flux. That is the rate of change of the flux is equal to this minus E, that is the induced EMF. So we can write like this. We will take the magnitude and we will calculate the rate of work done in producing a current I in the coil. So that is rate of doing work from the definition of power is equal to, we will take only the magnitude and we will drop the negative sign for calculation purpose. So EI. So this is nothing but from our formula you already learned, power is given by VI. So so that you know. So therefore, the EMF induced into the current at that instant in the circuit. So that is this. If you take the magnitude, so you drop this negative sign, I can write like this: L into di by dt into the current, or I will write a small symbol I. So that is Li di by dt. Now, so you can cancel out this dt on both sides. Therefore, work done for small increase in current di is given by L into I di. Now, suppose the current is increased from 0 to some value I. Then the total work done is given by integral of this dw, and here that is integral of Li di from 0 to I. So integral of I di is equal to I square by 2. Hence I can write like this. So that is equal to L I square by 2. Because there is nothing but, so that is equal to L into integral of I di. So which is equal to L into I square by 2, or W can be written as half L I square. Okay, so you compare this with kinetic energy formula in mechanics half mv square. You can see the mass and L are in the same position. So we can say that self-inductance is equal to mass in mechanics, which is responsible for inertia. So this is the formula for the energy stored in an inductor or a coil. If it is carrying a current of I, then in the form of magnetic field, energy will be stored in the coil. So that is given by this formula of Li square. Then suppose if there are two coils and mutually inducing each other the current or EMF by induction effect, the flux linkage between the coils or the flux linkage in any one coil due to the current in the other coil. So we can write like this: flux linkage, that is say N1 Phi1. So for two coils which are nearby, or we can say for two nearby coils. So for two nearby coils, the flux linkage is given by the inductance, that is the first coil, and the current passing through the first coil, plus inductance of the second coil with respect to the first one, and this is say some current in the second coil. So actually, or we can say 1, 2. So mutual. This is self-inductance. This is mutual inductance. Hence, you can write like this. So this is actually Li1 and this is Mi2. Therefore, the induced EMF will be minus L into di1 by dt and minus M by M into di2 by dt. So, when two coils are near to each other and are carrying currents, one will induce or one will produce a magnetic field in which the other is present. So, the magnetic flux linkage will be due to two reasons. Due to the current in the same coil, a magnetic field will be changing, that is self-inductance will be taking place, and due to the current changing in the nearby coil, mutual induction will be taking place, that is induced by the current in the second coil in the first coil. So a current will be induced in the first coil due to changing current in the second coil. So that is mutual. So both self and mutual inductions will be taking place in the nearby coils if they are kept side by side and currents are changing in both the coils. Therefore, the flux linked with both the coils is same. So you may calculate the flux linkage of one coil with respect to the other. It will be same for both the coils. Hence, we can write like this. So one is the self-inductance, the other is mutual inductance. So you will calculate the mutual inductance of first coil with respect to second or second with respect to first. So it will be same, both are equal. That is what I have shown earlier. So this will be the total induced EMF in the coil because of self-induction and also because of mutual induction. So we will discuss next about the AC generator.